Today we will discuss current source inverters. So first we need to understand these are current source inverters means these are simple inverters with current as the input source. Okay, so inverters means first we should understand it is the conversion from DC to AC. So now how these current source inverters are existing and how these current source inverters are different from voltage source inverters, what generally people used to pronounce and used to discuss. Okay, so these things we will discuss in this video. So let's move on. Yeah, inverters, DC to AC converter conversion. So what exactly the current source inverters? So till now maybe we may mostly pronounce the voltage source inverters. That means voltage source inverters means where voltage is the source, that means voltage will be constant. So coming to current source inverters, the current from the DC source is maintained at constant level irrespective of load and inverter conditions. So see here, current should be constant. Current is maintained constant at source side. So source side means it is the DC current. Then what will we achieve? So this is achieved. So how can we do this? This can be done by inserting a large inductance in series with the DC source. So this can be done by inserting a large inductor in series with the DC source. Okay, why this happens? So what will happen if we do that? So if you do that, the changes of inverter voltages to be accomplished at a low rate of di by dt. Okay, this part is very important. That means if you do that, the current is almost constant. Low rate of di by dt means it is the change in current is almost very less, so the current will be almost constant. Okay, so how can we achieve this? This can be achieved by inserting a large inductance in series with DC source. Okay, so this is the basic structure. So the basic idea of inserting the large inductance is to incorporate low value of di by dt with the inverter voltages. So this is the main idea. So now what exact generally happens? So generally what happens means we are getting DC supply from AC input supplying through a controlled or uncontrolled, maybe diode, bridge rectifier, rectifier. So what will happen if we do this? So if we do this, if we take DC from AC by using controlled or uncontrolled bridge rectifier, we will definitely get DC, maybe with pulsating DC. So how can we make it pure DC? We need to use L filter there. L filter there, and this L filter again resembles this inductance. Okay, and this L filter and this inductance are same, so we need to keep this inductance as large as possible to make the current constant. Okay, this is the simple concept in this. So now obviously why we are using L filter, this part we know. This is to make it ripple free, to make the current ripple free, so we are using L filter. So now what is the advantage of this? This advantage is as we are getting constant current here. Okay, so what will happen? We can use it for very high power factor loads. So we can use it for very high power factor loads. So what exactly meant by this? So power factor means it is maybe power factor angle. Okay, power factor power factor generally depends upon power factor angle. That means the power factor angle is angle between voltage and current. So what will happen to current? So current generally depends upon the voltage, sorry, generally depends upon the load. If there is any non-linearity in load, okay, or any inductance in load, then what will happen? So definitely we are getting deviation of the current angle from voltage. So there is a voltage difference between the voltage and the current, sorry, there is a angle difference between the voltage and the current. So definitely because of that we are losing some power factor. Okay, so with this we are unable to work out for very high power factor loads if we use voltage source inverters. But coming to current source inverters, we can go ahead with very high power factor loads because the current is almost constant. So this is the basic idea of current source inverters and main application of current source inverters. Now let's move on to the applications. What are the different applications of current source inverters? The applications are very huge, so we will see the different part of applications where the normal things are unable to get it. I'm sorry, I will take some other color. So coming to applications, applications means this is a DC to AC converter, so it can use it for the speed control of AC motors. So the first application comes with speed control of AC motors. And the next application is induction heating. Induction heating. And the next one is lagging VAR compensator because it gets very good high power factor load. So we can go ahead with the lagging VAR compensator. We can use this one as lagging VAR compensator. We can use it in compensation technique. And synchronous motor starting. So it can be used as synchronous motor starting. So these are the really the typical examples of current source inverters. And now we will move on to how best we can discuss this current source inverters. What is the application and those things we will discuss. And one more thing I have to tell you here, current source inverter may be load commutated or forced commutated. So if it is load commutated, we no need to provide any extra forced commutated circuitry. But if it is forced commutated in a CSI, definitely we need to provide the forced commutation kit. Circuitry should be there. Okay, of course it will again adds cost to the CSI. So coming to which part, I mean which things are used with the load commutation and which things are used with forced commutation. So load commutation is generally used for the leading power factors and forced commutation is generally used for the lagging power factor. So generally, frankly speaking, we have dealing with more and more of lagging power factors only. So we should definitely require forced commutation. Okay, in general applications. So of course load commutated, this part is also there for leading power factor. So now we will discuss the load commutated CSI only. Okay, so we will go ahead with the single phase capacitor commutated CSI. Capacitor commutated CSI with resistive load only. Okay, we will make it simple. So let's move forward. Yes, so I will write heading here. You just observe it should be the single phase capacitor commutated current source inverter with resistive load. So how it will be? Okay, we will see. We'll draw the diagram and then we can move forward. It is very simple as we have already discussed. I am not drawing any AC source here or any rectifier here, so I am directly getting the DC, and it should be connected through a very high large inductor, and it is connected to thyristor. Again one more thyristor. Of course, this is just like full wave bridge inverter. You can see this. So I'm not drawing load here. You can just observe the structure of this with single phase full wave bridge inverter, so that you can easily understand this. Yes, now I am drawing the load. So in between these two, load should be there, and you can see the load is a parallel combination of capacitor and the resistor. That's it. So now we can give some names for this. Yeah, this is EDC, and this is a large inductance L, and this is the thyristor T1, and this is another thyristor T2. This is one more thyristor T3, and this is another T4, and resistance load R and capacitor C. That's all. Then how to deal with it? So how can we deal with it? And this can be called as constant current source, okay, with this voltage source and in series with the inductor, we can call it as the constant current source. So this is the constant current source here. So let's move forward and what exactly happening here. So I will explain the operation first, later we will see the other parts. So the operation will be very simple. See, whenever before t equal to 0, so what will happen? So before t equal to 0, I want my voltage across capacitor, this is plus and this is minus, this is Vc. So voltage across capacitor should be minus E1. Okay, so I have charged the capacitor in the reverse direction, keeping this part positive and this part negative, and this part I can call it as E1. So in this way I have charged my capacitor previously. So whenever t equal to 0, so I will give firing pulses to T1 and T2, so that the current is passing from EDC inductor and T1 and combination of resistance and capacitance and T2 and back to EDC minus. Let me call it as EDC plus. So I can show you this diagram. I can show you with points also. So let us see how it should be. Yeah, it is coming from this. Current is coming like this, and again current is dividing into two parts here. One part from that and one part from load, and again it is joining here with T2. It is again coming and reaching the EDC like this. Again it is joining. Okay, this is exactly what exactly happened in the first off cycle. So let me take this part from 0 to t by 2. Okay, from 0 to t by 2, this is what exactly happened. If this is the case, then what will happen? So if this is the case, actually as previously I have E1, my capacitor is charged to E1. So if you can see, the plus is connecting to T2 and T3. So whenever t equal to 0, what will happen? How can you provide gating pulses to T1 and T2? Okay, they should be forward bias, right? So I will show you the forward bias of it. So this is the negative, this is N, and it is touching minus, so this is in forward bias. T1 is in forward bias, and this is P. For T4 it is P and it is connected to minus, so this is in reverse bias. So what exactly happens here? So here this capacitor makes T3 and T4 reverse bias and T1 T2 as forward bias. Okay, and what will happen during this? So during this period the capacitor is gaining the voltage from minus E1 to plus E1. Why? Because now what is happening? Current is passing through this capacitor. Now capacitor is getting charged in this direction, in plus and minus direction. So this minus E1, maybe you can take some value for E1. Okay, it will charge up to that level. Okay, after charging that level we will remove the firing pulses to T1 and T2, and automatically T1 and T2 will become reverse biased and T3 T4 will become forward bias because of plus E1. So why the T3 and T4 are reverse biased if the direction is plus and minus? With the same reason T1 T2 become reverse bias with this plus and minus, because these two are reversed. Okay, so now in this connection I can explain. Now let me go ahead with T by 2 to T. So what will happen? So for coming to T by 2 to T, what will happen means the capacitor is charged to plus E1. So because of that capacitor, T1 T2 become reverse biased and T3 T4 become forward biased. Now I am giving the firing pulses to T3 and T4 so that the current direction will be EDC plus inductor T3 T4 back to EDC minus. So this is the direction, you can see T3 through capacitor, after that T4 and back to supply. Okay, this direction is also there through resistor. So this is the way it is going ahead. Now let me consider load. Let me consider the voltage across load. This is my resistance, and if I take plus and minus and V0 from 0 to T by 2, what will happen? It is positive in nature. V0 is equal to positive plus VE. Okay, and this, for example, this plus is touching T. If from 0 to T by 2, T1 and T2 are forward biased, so current is passing like this, touching positive here. This is V0, touching positive here and going through negative, so it is positive. Coming to T by 2 to T, it is coming in this direction now, in this direction, so touching negative first, so V0 will be negative. Okay, this is regarding output voltage. Okay, so now this is the simple explanation for our single phase capacitor commutated CSI. Here the main thing is, this is just like full wave bridge inverter only, but here because of the capacitor, so we need to understand how nicely it is commutating the other thyristors. Okay, so this is the simple concept. So now our job is to draw the circuit diagram, waveforms. So let's move on to the drawing of waveforms. So yeah, you can, I like to use this part only. Yes, so let me use this part. So please take this as y-axis, this is x-axis, and this red line as the y-axis. So what exactly happens here? It is IZ1 and IZ2. So how we are giving gate pulses here? From this point I can draw one line. So this is T by 2 line. From this point I can draw one more line. This is T line. This may be 3T by 2. This is 2T. So first I am giving gate pulses to T1. After that I am making it off and then on. So it is very simple. I can show you. Yes, this is for here T1 and T2 are on. Here T3 and T4 are on. So T1 and T2. Again T1 and T2 and T3 and T4. So in place of okay, this is the condition. So let me draw this line. So this line is for T3 and T4 gating pulses IZ3 and IZ4. So IZ3 and IZ4, so gating pulse has been given like this now. Okay. So these are the gating pulses. So first we need to give gating pulse to at t equal to 0. At t equal to 0, the gating pulse should be given. This is 0, this is t by 2 and this is t. This is again 3t by 2. This is 2t. Simple. From 0 to t by 2, t1 and t2 are on. From t by 2 to t, t3 and t4 are on. And these are the responsible persons to make these two, these combinations on in this way. So now let's move forward and we will quickly draw the figures. Next, what is current passing through thyristors 1 and 2? So current passing to thyristors 1 and 2 will be just similar to this. Current passing through thyristor 1 or 2, both are same only. So it is exactly equal to, whenever it is on, current passing through this is same like this, but the current value here is I. Okay, let me go back. If this value is I, whenever current passing through T1 and T2, the current is same. It is series connection. So current passing through T1 is I and current passing through T2 is also I. That's all. Now how to deal with the E1 and L1. So here you can see. Now I am dealing EL, so load voltage or V0 or EL. So whatever it may be, you can write, not an issue. So in textbook it is EL, so you can maintain with EL or V0 also, not an issue. So let me go ahead with V0 only. V0 and I0 both are same because it is in resistive load. So what exactly happens? So it is happening from minus E1 capacity charging, from minus E1 to plus E1. Okay, so this is E1 and this is minus E1. So it is happening like this. In this way it is moving. Okay, so what happened to capacitor current? So how the capacitor current would be? So the capacitor current would be, it is reducing, after that it is negatively increasing, again it is reducing, it is again negatively increasing. Of course these two are same. Okay, so this is the current. So I can say that this is current IC passing through capacitor. Now what happened to EDC? Okay, source voltage. So how the source voltage will be? So as source current is constant here, so I don't mind, I can't say that source voltage is constant. So source voltage will be like this. It is increasing, later it is, so sorry, once it is increasing and after that it is decreasing. We will see this. Okay, EDC is, this is also like increasing, then again it's coming 0, and it is increasing like this, again it's coming 0, it's increasing like this, again it's coming 0, it's increasing like this. Okay, this is like almost equal to here voltage only, I mean uh, load voltage only. Okay, it is almost like load voltage only, but with small curves because of inductance. So then how to draw voltage across thyristors? So I can draw voltage across thyristors also here. You can see, yes. So now voltage across thyristor I can draw here. So how this would be? So this would be also very easy. Voltage across thyristor. So if you can see here, thyristor voltage, yes, current passing through thyristor, as from 0 to t by 2 current is passing through thyristor, the voltage will be 0. So after that what will happen? After that the voltage will be equal to source voltage. So what is source voltage? This part is the source voltage. So this part whatever we have written is this source voltage. So this part is source voltage. So after that this part is appearing. Again it will be 0. After that this part is appearing. Very simple concept. So from 0 to t by 2, the voltage across T1 will be equal to 0 because current passing through that thyristor. So later it is maintaining like source voltage only. After that again it will be 0. Later it is maintaining like source voltage only. Okay, so this is very simple concept, so you can easily understand this. So if you have any doubts you can ask me. So yeah, I want to tell you one thing. So whenever you are dealing with DC, you need to put, I mean your, if your input is AC, you have to write omega t. If your input is DC, you have to write t. Okay, this part also please keep in your mind. And if your input is AC, if your input is AC, your time period is from 0 pi by 2 pi, okay, 3 pi by 2, 2 pi, like this. If your thing is only t, so it should be 0 t by 2 t, 3t by 2, 2t. Okay, please don't confuse, it is very very simple concept. If you are based on your input you have to deal with it. Okay, so if you have any more doubts you can put it in the comment window. I will answer you within 24 hours. And if you have any problem in it, just you can see the, you can refer the textbook also. And still if you have any doubts please come to me. So thank you so much for your careful listening, and in the next video I will discuss the difference between VSI and CSI. Thank you so much, and please subscribe to our YouTube channel, and please like this video and share this video with your friends and family. Thank you so much.